Well, let's get started, everyone. Hopefully I've got the thing in the right place. We're looking at derivatives as functions, and in particular, we're going to do a few more examples of sketching derivative functions from the original f of x. I've got the beginnings of a migraine coming, and so in my case, I tend to get what I call fireworks, and my vision goes a little bit, and I get distracted. So giving you a heads up, if I feel that I seem even more distracted than usual, it's because my focus is going a little bit. But I got my medicine, which is tons of Pepsi, and I've had my ibuprofen. And I'm very lucky because when I get migraines, they typically only last half an hour. So I'll be over it soon. So here's the kind of question we're going to be dealing with. Imagine I give you the sketch of a function and y equals f of x. It's going to go here. And underneath, we're going to do a simple sketch. It's not going to be that accurate of what the derivative looked like. And if I remember yesterday, did we do like a polynomial or a cubic function? I think we did one of them. Have I done straight line ones, right? Functions that are made up of straight lines. Have you seen that yet? No, okay, that's the one we'll do right now. So I'm going to have a function made up of various straight lines. There we go. And when a function is made up of straight lines, the way that you're going to approach sketching this derivative is that you're going to find corners. So I'm just putting those circles around. Now, these corners are going to how you split the shape up. One of the common methods of doing sketches of derivatives is to find key places on the original function where something is happening to the curve. It's changing in some way. And corners are very often places where things are changing. I'm going to give each of these regions a number. This is region 1, this piece of the curve. This tiny little bit in the middle is 2. This flat bit is 3. This sloping bit is 4. And this sloping up bit is 5. So we've got regions 1, 2, 3, 4, and finally 5. Now, in each region, each piece, we kind of treat on its own. This piece of the curve is a horizontal line. If you pick any point on that line, would you agree the tangent line is also horizontal? I mean, it's on top of the line, but technically it's horizontal. So in this region, region 1, the derivative, the slope of the tangent line, is going to be the fixed number, and that number is going to be 0. So what am I going to do? Green, I think. So 0. And an open circle there. Now in region 2, the line is sloping downwards. So every point on that line has a tangent line pointing down the way, which means it's the same number, but it's negative below the x-axis. And so it's going to be this guy. What about region 3 then? What will the derivative be in region 3? Any takers? What's the slope of the tangent line from here to here? Come on, guys, You're giving me a migraine. Right, someone said something and I talked over them. What was it you said?
0.
0. And so you go 0 again. And then in region 4, it's pointing down the way. So you go negative again. And in 0, 5, it's positive. So you go up again. Now you notice that each of these corners, there's a distinct break in the derivative. And whenever you get a break like this, open dot on both ends. So you're not going to see any solid dots attached to any of these lines. And that's going to be true all the time, because at a corner, the derivative doesn't exist. Doesn't exist coming this way, doesn't exist that way, because at the corner, there's not a single value for the tangent line. And that's what you get if you want to do a straight, a graph made of nothing but straight lines. Next one I'm going to do is the derivative of a graph that has vertical asymptotes in it. So I'll make my asymptotes green. Typically, I would make them red, but let's say I have a vertical asymptote at 3 and a vertical asymptote, let's say, at 7. And here it goes up, and then it horizontal like that, and then it goes and does this, and then on this side it does that. And that's our original function, f of x. And now we're going to try and sketch what its derivative would look like. Try and get that matched up. Okay, there are a number of features that vertical asymptotes that are going to help us. The places of interest, right? The places where I'm going to drop these little red lines downwards are actually going to be where the vertical asymptotes are. So I'm going to do an x equals 2. And then over here, I'm going to do an x equals 7. And that breaks my regions into region 1, middle bit region 2, and the end piece region 3. Now things are a little bit trickier to interpret this time. Let's do the curve here, right? This piece here in region 1. There are two different features going on. If you're picking values of the function x coordinates over here where my finger is, isn't the tangent line almost horizontal and getting closer and closer to being horizontal? So that means that as you pick values of x going this way, the derivative is going to get closer and closer to 0. Now let's look at values here. Would you agree that these are all positive tangent lines, right? So I know everything's above the axis. But as I get closer to x equals 2, that might have a tangent line of 5. Then a little bit closer, it's now 10. And a little bit closer, it's now 2 million. Can you see that as you get closer to here, the derivative is positive and it's getting bigger? So vertical asymptotes on an original function generate vertical asymptotes on its derivative. So far, so good. Now, let's look at this curve. If I choose any point, let's say I chose that point, wouldn't the derivative be that line? And isn't that line negative? It's slowing down the way, right? From left to right, it's going down. So every point on this curve in region 2 is negative. That means that it's all happening down here. As you get closer to the vertical asymptote, Instead of being -5, it becomes -10, it becomes -1,000,000. It is negative. So the original function had a vertical asymptote that I call a volcano. That's the ones that zoom up on both sides like that. But do you notice that the derivative had a vertical asymptote, but quite different shape? Now, what's going to happen here, right? Well, the derivatives start off like 5, then they go 4, -3, -2, and so on. So they stay negative, but they get smaller. And then they start picking up speed again. -1, -2, -3, -1,000,000. So the net effect of that is that happens. So you see, it's a much more complicated situation when you're looking at these things, because you're trying to imagine what the slopes of the tangent line at various points are, and trying to detect a pattern, like on this side they get really big and negative, on this side they get really big and negative, but they kind of, you know, change over there. Right, one last piece to get. Region 3. If I choose any number at random, like these little snapshot guys here, would you agree that at that point there, the tangent line is very big and negative? In fact, if you choose any point, they are all negative, although towards the end, don't they get very close to being 0? So very close to being 0, but then get much bigger and negative. Whew, there's our shape. So doing the sketch of a function that has vertical asymptotes, doing a sketch of its derivative, is a little bit more complicated than most. Any questions so far? Are we good? I'm going to see if I can show you a homework question similar to what we've been doing, so you get an idea of, you know, kind of how they do it. Never find things when I want them. So. Come on. Oh God, they're ugly ways of doing it. Never mind. Here we are. I don't like the way the homework question kind of makes the question happen, or kind of shows you. So here we go. This is question 2. It says match the graph of each function a to d with the graph of its derivative 1 to 4. So these 4 guys are the derivatives, and these 4 blue guys are the original functions. I think it would make much more sense, wouldn't it, to give you the original ones at the top and then the derivatives underneath. But yeah, we can live with that. Okay. If I did question B, do you see a zigzag one? Right, that's the original. What would its derivative look like? Well, the corners matter. Here, the function is sloping upwards, so I would expect a horizontal line. Here it's sloping downwards, I'd expect a negative horizontal line, and here it's sloping upwards. So I would expect to see horizontal, horizontal, horizontal. So I would go up here, and there you go. Can you see picture 1 is what I just did? So the way that you get these questions in the homework is they give you a curve like this guy. So this one looks like a big M, right? Imagine this M shape. Which one of those 2 guys do you think would be the sketch of the derivative of that big M? So I'm making it easy by only giving you 2 to choose from.
Number 4.
Correct. And you could check it, but it is. And let's see. Now, here is a slightly different way of doing it, maybe a little bit better. It says, trace or copy a graph that looks like that. So you just got your paper and you do a big smiley face with curls at the end, right? And then you would do its derivative. And they do it by giving you the original picture and the derivative on the same diagram as they have here. So the original one is the blue and the derivative is the red. So if I was looking at this function here, 0, 0, and 0. Well, that one's not good. Original function should have a 0 there. Yep. The original function should have a 0 there. And the original function should have a 0 there. So I would say that one. And here's a function. Pick its derivative. Oh, I should do that one. That was a good one. This one will surprise you. I'm going to do the derivative of a function that is basically half a circle. So that's my original function, half a circle. And we're going to figure out what its derivative is. Not an awful lot going on here because the function essentially just stops, right? There's like end dots. So I'm going to go and find that point there is probably the only point that's of any interest because at that point there, the tangent is 0. So that splits this shape into two distinct regions. Region 1 is this piece of the curve. Region 2, this piece of the curve. And I know right there at x equals 0, the derivative is 0. So that's what the dot is. The value of the derivative is nothing there. Right, now if you look at this piece of the curve, as you get closer to x equals 0, the tangent line gets less. You know, it may be 1 and then it's a half and then it's a quarter, right? It keeps on getting smaller. So I know that it's going to home in and I know that it's positive. Right? So I know it's going to come in something like that. Now, if you take region 2, aren't all the tangent lines negative? So I know they live in here, but I know as you get closer to x equals 0, the tangents get smaller. So I know it's going to do that. Now I've got essentially the function finishes here and here. This is where it gets a bit trickier. As you pick values of x closer to the edges, notice what happens to the derivative, right? It's positive 4, right? As you get a little bit closer, positive 8. As you get closer to the edge, positive 10. Oh. Right at the end, I don't know if I've drawn it well, but you know when you've got a circle and it comes down and it finishes, right at the end, isn't the tangent line vertical? Which means that it is infinite, and infinite as in positive. And the same argument here, it's negative, 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 and very negative. And so it's infinite going that way. So in this question here, do you see that your derivative looks a bit weird? The original did not have any vertical asymptotes, yet the derivative does. Next one is straight lines, which I've done, and next one is curves I've done. So I've pretty much, I think, covered what the shapes of the derivative of a function would look like if you're given the first one. Any questions before we close the door on chapter 2? Great. Well, we're now going to get a little taster of chapter 3. And we are going to be looking at derivatives, polynomials, exponentials, and trig functions. So we have seen the end of the limit as x tends to a and the limit as h tends to 0. We are now going to get derivatives by using various rules and laws and basically just memorizing things as well. So let me start with a guy that we should be familiar with. Polynomials. Don't we have a rule called the power rule that allows us to find the derivative of a polynomial? And the rule basically says multiply by the power and then reduce the power by 1. So multiply by the power and reduce the power by 1. Multiply by the power and reduce the power by 1. And then for these two guys, we kind of make up special rules for them. Technically, they are both power rules as well, but it's easy to think of them differently. What's the rule for things like plus 3x? What do you get if you differentiate plus 3x?
3.
Yeah. And what do you get if you differentiate a number like minus 1 or plus 1?
0.
0. So we have a very, what would I call it? Would you get it's a very stable rule, isn't it? An easy rule for differentiating polynomials, right? Multiply by the power, reduce it by 1. So far, so good. So imagine I said that I want you to find the equation of the tangent line It's a bit hard for me to focus right now. The equation of the tangent line to this function at the point P, 1, 3. So I've defined the equation of the tangent line to this polynomial at the point 1, 3. First thing you're going to do in questions like this is you're going to find the derivative, which we've already done, so I'm just rewriting it. Step 2 then is you're going to find the slope of the tangent line. At x equals 1 in this case. So the slope of the tangent line is going to be the derivative at 1. So that's going to be 15 times 1 to the 4, take away 4 times 1, add 3. That's going to be 15, take away 4, add 3, and I hope that's 14. Does that seem pretty straightforward? That's what you would have done if I hadn't told you to do it, right? Find the derivative, because that's going to give me the slope of the tangent line. Evaluate the derivative at whatever the x coordinate is, in this case 1. And now I know the slope of the tangent line, which I'm calling m. And then step 3, we use an equation that is very often called the point slope equation. Hopefully you remember it. Y minus y1 is mx take away x1. Okay, remember that is the formula for getting the equation of a line that passes through the point x1, y1 and has a slope of m. Remember that, guy? Point slope equation. Now, in our question then, x1 is 1, y1 is 3, and m is 14. So we're pretty much good to go here. It's going to be y take away 3 equals 14 x take away 1. And then, you know, for completeness sake, you make it look pretty. So 14x take away 14 by distributing. Add 3 to both sides. And there you go. Now, if I had time, which I don't really want to spend the time right now, couldn't I check that on Desmos? Now, what I would do in Desmos is I would put in this original function, and can we pretend that it looks like that? And then I would find the value of x equals 1, and it would be there. But when I type in my line, wouldn't my straight line look like that? And if I did it right, wouldn't there be a perfect tangent line at the point 1, 3, right? That's how I could physically check that I've done everything correctly. Are we good? Right. Let me show you another way to check. And this is only to check. So I'm going to go to my calculator. I'm going to go y equals, and I'm going to type in the original function. So it'll take me a few moments. 3x to the power of 5, and subtract 2x squared, add a 3x, and subtract 1. Nothing special about that. Make sure your window has got 1, 3 in it. So as long as x has 1 in it. So I'm just going to go from 0 to 2. And then if you do zoom 0, you can get a little idea of what the sketch looks like in that region. Doesn't look particularly interesting. Now here's the check. Blue button, trace, second calc. Now down here in number 6, there's a funny looking guy called dy by dx. You see that guy? dy by dx is another notation for the derivative. So if you ever see that, it means the same thing as that. So I'm now going to hit enter. And it's got to whatever it is down here. I want to type in x equals 1 and press enter. And do you see 14.0000 and stuff? Do you see that? It's just told me that the slope of the tangent line is 14. It's not perfectly 14 because it's doing it numerically. It's not doing it like we would do it as humans, right? It's doing an estimate. But it's a pretty good estimate, do you agree? It's 14. And that's how you can find your derivative, or at least a check. And no, you are not allowed to say, well, I can go and do Calc 1 dead easy. I'm not going to listen to any of the rules that he's going to give me in the next 3 weeks, because I'm just going to plug into the calculator, put in x equals 1, and the answer's 14, and I'll be able to stick 14 into WebAssign and get the right answer, and gee, aren't I clever? No, you are being very stupid, because if you let that calculator take over, you will not be able to prove to me or show any of the working that you need in an exam. And your exams are worth an awful lot more points than your homework is. And so you will fail the exams and you will fail the class. So that trick I just showed you is a check. It's just a way of making sure that you've done it right. It's not a replacement to all this good stuff, right? Well, that's polynomials. Let's show you some new guys in town. I would like to be able to differentiate that guy without having to do the limit as h tends to 0. Because if I had to do that, wouldn't that be one of those conjugate methods and it would take me forever in the day, right? I don't want to do that, right? So This is how you find its derivative. Rewrite it as a fractional power. So try in your mind, a square root is a half power. A cube root is a 1/3 power. And forever and so on. A 4th root is a 1/4 power. What would the 4th root of x cubed be as a fractional power of x? The 4th root of x cubed.
3/4 or x to 3/4.
Okay. Now, step one then. If ever you have to deal with square roots, cube roots, 4th root cubes, all that stuff, turn it into a fractional power. Now here's the cool part. Remember the power rule was multiply by the power and then reduce the power by 1, right? The power rule also works when the power is a fraction. So multiply by a half and then reduce the power by 1. Well, a half take away a 1 gets you -1/2. So far, so good. Now we enter into style points. Style points are big. We need to be good at them. And the rules for style points. 1, make the answer look like the original. 2, factor the heck out of it. And that includes collecting like terms and all the other good stuff. And rule 3 only applies to trig. If it's a trig function or expression, use trig identities when you can. So if I did a function and there was, sines and cosines in it, there are some trig identities that we expect you to know. Suppose I ended up with sine squared x plus cos squared x. What would that turn into? Sine squared x plus cos squared x. What would that turn into?
Isn't it 1?
It'd be 1. Suppose I had a sine x, a fraction, sine x on the top, cosine x on the bottom. What would that turn into?
Change in mix.
Right. So you know that you're going to have to be in the lookout for trig identities. Right now, that ain't a factor because we don't have trig. So I have to do rule number 1 here, which is very common. Make the answer look like the original. Well, first thing I'm going to do is I'm going to use a piece of algebra that we use a lot, and that is negative powers can be rewritten as a fraction with a positive power in the bottom. So -2, x to the -2 is like 1/x², right? So x to the -1/2 can be written like that. And can x to the half be turned into a square root? And now we are finished. So this is what we would expect the answer to be. Now, if you say, well, why do I need to worry about this? Look, I got the answer. Can't we just all be friends? No. Well, we can still be friends, but no, you're not allowed to stop there. There are a number of reasons why we tend to be so precise and pernickety. In mathematics, we are very much rule orientated, maybe sometimes to the point of being like over rigorous. But side issue, we never write 1x, don't we write x? Everybody's agreed that you don't need a 1. Right, that's an example of style points. If it was 0x, wouldn't you write 0? Except if it was something like 7x plus 0x, wouldn't you just write 7x? Isn't there a rule that you don't write zeros down if you don't need them? Right? That, just to give you an example of some of the rules that we have. Right? The background behind this is that mathematicians, when they do something really complicated, not this isn't particularly complicated, that if we all end up with the same answer, and the same answer looks the same, in other words, we all turn them into the same thing, it's dead easy to compare our results. See, if I did this and someone in China, I don't even understand Chinese, but they would get the exact same answer. Everybody who's a mathematician realizes that this is what the answer should look like. So that when I look at someone else's work and they're a mathematician and I see their answer, I know exactly, yep, I know where you got it. But, you know, if some places decide to do this and other places decide to do that, and then third places start doing that, don't we have the big problem was, well, that's your answer. Now I'm going to have to figure out if it's my answer, right? Because you have to keep changing it. Now, when expressions get really big and really ugly, that does become a major issue. Because you could write a really messy expression in lots of equally messy ways. In which case we'd be spending half our time checking each other's work to make sure that they were the same answer as the one I got. Whereas if you all finish at the same destination, doesn't that make life easy? So try and sell it. Style points are the big thing. Do them. Well, that's square roots. Let's do, oh, let's change the letter to G. Let's do 3 cube root of x to the 5. That's a pretty ugly looking expression. First thing I'm going to do is to rewrite it as a fractional power. And now I can differentiate. The power rule says multiply by the power. Well, that times that gets you 5. Reduce the power by 1. 5/3 take away 1 leaves you with 2/3. Right, style points kicks in. Once you finish with derivatives, from this point onwards, it's making it look good. Does that look like the original? Yeah. But this one's going to be pretty easy to convert. I don't have too many lines to do that. How would we write x to the 2/3 to look more like this radical? What would it be?
The cube root of x squared.
Boom, done. That wasn't too bad. Now, everything I've said up to this point is correct. I just want to show you something.
So on the exam or
Yes.
the midterm, on these questions, would we be allowed to use the power thing and not show our work for it?
Depends on the question. So if I just say find the derivative, you can use the power rule. If I say use the limit as h tends to 0 of f of a plus h, you know that one. If I say use this rule, you have to do it the long way.
Okay, so if it says like use the rule with all the h's or the rule without the h's, show your work.
Yeah.
If it doesn't ask for that, use the power rule.
Yeah.
Okay, thank you.
So if nobody says you must use, here's the formula you must use the power rule, definitely. But imagine that was my question. There's my answer. All right. In this question, according to the rules, doesn't that look like the original? So this is correct. So do you see how the style point rule, make me look like the original, could mean different versions of the same answer depending on where you started, right? So you don't need to turn that into this. In fact, you probably shouldn't, because isn't this the answer that looks like the original? Okay. How about this fella? I would like to be able to differentiate simple fractions, right? 5 over x squared, 10 over x to the 4. Right? I want to differentiate them. I don't want to do it that long with God. Can you imagine trying to do it, you know, Monday's way? Wouldn't that be horrendous algebra, right? Really ugly. We want to do it a shortcut. Here's a piece of algebra that's allowed. Can't negative powers be written as fractions? But can't fractions be rewritten as negative powers? Do you see they work both ways, don't they? Now, the advantage of writing it this way is can't we now use the power rule? And the power rule says multiply by the power and reduce the power by 1. And I almost did this. I'm glad I stopped myself. I was about to put -3. But that's not right, is it? What number should I be putting in?
-5.
Yeah. If you're not careful, as I almost was there, can't you sometimes say 4 becomes 3, right? Because if it was +4, it would become 3, right? But -4, when you take 1 away from it's -5. Right, according to the style point rules, which in our case is make it look like the original, and that doesn't look like the original yet, but it's only a one-liner. Would you agree it's pretty easy to fix? And it's -40 over x to the 5, and now we are happy. So I can use the power rule to do square roots and cube roots. I can use the power rule to do simple fractions. Pretty cool. How about this one? Oh, short of paper. Last one. I want to differentiate that even uglier fraction. Can someone tell me what that would look like in a form that's going to allow me to use the power rule? Because right now I can't use any rule.
10 times x to the -1/2.
For those who want to see the intermediate stage, wouldn't you call it that first and then get what you just said? Now, in that format, isn't the power rule allowed? So multiply by the power and reduce the power by 1. Derivative is now finished. From this point onwards, it's all about style points. First thing I would do is rewrite the negative power. Oops. I'm going to write that again. Is rewrite it as a positive power. Are we comfortable about that piece of algebra? Negative powers of x can be written as fractions with positive powers. Okay, almost done here. So it looks like the original. How will I rewrite x to the power of 3/2?
Square root of x cubed.
Style points, finished. Stick a fork in it, it is done. This power rule is pretty versatile, isn't it? It doesn't just get you, x cubes. It gets you fractions. It gets you square roots. It gets you, 10 over square roots and all sorts of cool stuff like that. Pretty resilient. Okay, your last name. Your